It's my pleasure to introduce to have at our seminar Matija Bucic, who is now a professor at University of Vienna, and before that he was in Princeton and ETH with Benny,
Yep.
and who recently received the European Prize in Combinatorics, right? So congratulations on that, actually. Yeah. And Matija will talk on equiangular lines, some new exciting progress.
Yeah, so thank you very much for the very kind introduction. Thanks for having me. Okay, so so I want to tell you about a problem which I really like, which sort of sits in between two areas. So on one hand, it's a geometric problem, but it now kind of is understood to have a lot to do with also certain very nice spectral graph theory problem. So everything I'm going to say is joint work with Igor Bala, who has really done some spectacular work on this topic, and you'll see his name popping up quite a bit as the talk progresses. So let me start with the geometric perspective and the kind of origin of the question and explain the main concept I want to talk about today, which is the notion of equiangular lines. So here, if you have a bunch of lines living in r-dimensional Euclidean space, we say that they are equiangular if any two of them define the same angle. For example, here is a collection of three equiangular lines living in the plane. So any two of these lines defines the angle of 60 degrees. So this is three equiangular lines. Now, of course, any two lines actually define two angles. So what I really mean is we are comparing the smaller of the two angles, or if you want, compare the set of the angles that they define. Or even later on, we will essentially be looking at the inner product of the unit vectors that define the lines. And also it's maybe good to point out that if you translate the line, then the angle with any other line that it defines doesn't change. So we are also free to just assume that all of these lines go through the origin, and we'll be doing that for most of the talk. Very good. So now one of the most basic questions you can ask about this concept is, well, how many of them can you actually fit in r dimensions? And this is a question that was first asked, as far as I'm aware, in the late 1940s in a series of 3 papers, which I do not really understand the independence graph, so I'm just stating the authors. And they came from the perspective of elliptic geometry, because in elliptic geometry, the question of how many equiangular lines can you fit in r dimensions actually corresponds to asking how big of a simplex can you build in a certain projective elliptic space, which is arguably one of the most kind of natural questions you can ask about the space. And this was their motivation, but I'm going to stick to the Euclidean world and the equiangular formulation for the rest of the talk. So I'm not very familiar with the elliptic geometry, and there is no knowledge assumed or required for this talk. So besides this kind of elliptic geometry origins, there is actually quite a few very nice connections to other topics, some of which we'll touch upon briefly as the talk progresses, but for most of them, I will not have time to go into them, but it's quite surprising actually that this simple and very nice question pops up in so many different situations. Very good. So now let me tell you what we know about this problem. So still the best known upper bound that we know is due to Gerzon from 1973, and he proved that you can't have more than r plus 1 choose 2. And this is really, really a very nice proof. It's like a 1-paragraph proof, one of the earliest examples of applications of linear algebra in combinatorics, so-called polynomial method, or one version of stating it is using polynomial method. And if you haven't seen this proof, maybe for the next coffee break you take, you can try to give it a go. It's actually a really, really beautiful thing, argument, and a very nice thing to think about. So also this R+1 choose 2 bound is tight in dimensions 2, 3, 7, and 23. And this sequence of numbers might be a little bit familiar because there is another very famous geometric problem, namely the sphere packing one, where very similar numbers pop up. And there it's 8 and 24, but actually the reason why the numbers are popping up is the same, because certain very nice algebraic objects exist, namely the Leech and the E8 lattice. And somehow here you just project one dimension down, which is why you get the 7 and 23. And also this is known for much longer than the sphere packing analog, and is much simpler to build the constructions in this setting from these objects. But still, it's sort of there is some nice connection going through that. And in general, if you kind of can build some other lattices with the same nice properties, you would kind of presumably get results in both settings. So here directly, and in the other one, it requires a bit more work. But this is the topic of the spectacular work of Vyazovska, and also Vyazovska and co-authors that resulted in her getting a Fields Medal recently. Very good. So in general, we do know that this quadratic upper bound is roughly the correct behavior. So this is thanks to some constructions coming from algebraic number theory due to DKN, which are actually reasonably recent. And since then, there has been several other constructions that achieve the quadratic order of magnitude. So in general, kind of the answer to this question is roughly understood up to a constant factor. We also know that if certain notoriously hard to construct objects exist, this will actually be tight. So from some point of view, there is of course various very nice interesting problems here, but this is reasonably well understood from my point of view. So what I want to talk about today is a question which has sort of became central in the area starting from the 70s, which is referred to sometimes as the relative problem. So the only difference to the previous one is that now you're not free to choose your favorite angle. Someone else comes and tells you you are forced to use 60 degrees when you're building your lines. Now, the motivation for this is sort of twofold. So on one hand, if you understand what happens in this setting, well, you also get the answer to the absolute problem. This is more general. You just look at all the possible angles, figure out which one gives you the biggest answer, and that's the answer to the previous question. And the second one is that actually some of the applications that I mentioned and connections to other areas do come with prescribed angles, so you don't get to pick your favorite one when you're doing that. So the first to actually introduce this question or write it down, it implicitly appeared in a few older papers than that as well, were Lemons and Seidel in 1973. And here I'm stating it with this peculiar choice of normalization, namely I'm asking for the maximum number of equiangular lines in r dimensions, with common angle being arc cosine of alpha. And you'll see in a moment why I'm choosing this normalization, because kind of the algebraic point of view on the problem will be much cleaner and will not involve trigonometric functions if I do that. So for now, just think of it, I'm giving you some sort of normalization on what angles you're allowed to use. So I'll call the answer to this question n alpha of r, and I want to tell you what we know about it. So the first kind of general result about it that was proved is due to Neumann. This is rather simple, nice algebraic proof that is somewhat different from essentially anything else afterwards. And what he showed is that if alpha is not 1 over an odd integer, then you get an upper bound of 2r. So contrast this to the quadratic answer to the general problem, and you can conclude that if you want to get this quadratic thing, your alpha better be 1 over an odd integer. And actually, we'll see that kind of in the case of 1 over an odd integer, we have only very recently started to be able to actually prove somewhat similar bounds to this. So over the years, people really focused mostly on this case 1 over an odd integer because the bounds that you could prove were nowhere near kind of close to this. And also, if you want to kind of beat linear behavior, you really need to look at this sort of behavior. I also hope that I'll show you a bit later kind of where this 1 over an odd integer is showing up. So far, it's a kind of mysterious thing, but somehow from the argument, you'll hopefully see at least some indication of where it's coming from. But I do want to say at this point that many of the things I'm going to say, I'm not going to maybe explicitly say, but implicitly they're assuming I'm talking about alpha being 1 over an odd integer. And the reason for that is to kind of simplify the story a little bit, because this 1 over an odd integer values are sort of the local maxima of this function. So if you're interested in kind of pushing it up, then kind of what happens in between is going to be smaller and is kind of going to be going up and down. And I want to avoid I want to simplify the story a little bit, and the picture is a bit smoother if I'm talking that way. I will once in a while mention what happens in between, and many of the things I do state in 1 over an odd integer do have analogs for other angles, but let me implicitly say from now on that alpha tends to be 1 over an odd integer whenever that's convenient.
Can I ask a couple of quick questions?
Sure.
Yeah. So alpha here is just the scalar product, right?
Yes, precisely. So we'll see that in a moment. That's why it's chosen in our cosine.
Yeah.
So
and for the lower bound, so I guess obviously we have something like at least R,
yes.
right?
Yeah.
Is there anything better than at least R?
So
like for these, for example, situations, like for any R, let's say.
So for when alpha is, I guess that's 0, so don't 90 degrees, then you will not be able to get more than R.
Yeah.
I think you can kind of maybe push it to R plus 1 in certain situations, and I'll get to some sort of general lower bound constructions or like bounds a little bit later. But
so this 2R is not like. So it might be actually like R plus 1 or something.
So maybe bear with me for a few more slides.
Okay, yeah, of course.
I think you'll get a bit better picture of what's going on here. But yeah, so this is just the kind of very first result sort of that was generally proving something nice here. But yeah, bear with me for a little bit longer. So I want to mention a little bit what happens in the low dimensional case, but I'm mostly going to focus on the high dimensional world. But actually, the low dimensional is very interesting. So in the original paper of Lemons and Seidel, they actually sort of determined what happens for this function when R is smaller than 1 over alpha squared, roughly. And the reason, and sort of what it does is it kind of is linear, and then it very quickly jumps to being quadratic. Somewhere around 1 over alpha squared, and this, whether it actually jumps to quadratic or not, this was not quite proved by them. They just have an upper bound, not the lower bound, but the lower bound is kind of has been proved later. So then there were two in the papers in between the two that I'm mentioning here, one by Yu and one by Glazirin and Yu, which sort of extended this Lemons and Seidel bound to go to some larger constant times 1 over alpha squared. And these were nice because actually, if you want to get this R plus 1 choose 2 behavior, your R needs to be equal to something roughly equal 1 over alpha squared. So there is only exactly one value that you can possibly hit R plus 1 choose 2 with. And it's somewhere around 1 over alpha squared. I don't want to write the exact function. And so what these two papers kind of did was they extended the range to include it and show that really if you want to hit that, you need to take exactly that value. And then what Igor showed is somehow how do you actually transition back from this quadratic to linear again. So this is what happens from the regime of 1 over alpha squared to roughly 1 over alpha to the 4. So again, if I write exact values of these functions, they're a little bit complicated. But the story for the low dimensional regime is that you're linear, you very quickly jump to quadratic, and then more gradually going to 1 over alpha to the 4, you again drop from quadratic back to linear. Now, all of these things are understood up to a constant factor. and also modulo existence of these strongly regular graphs, thanks to some of very nice results of Igor from this paper from 2021, you actually get exact answers for various things. Again, there is some dependencies on existence of these notoriously difficult to build algebraic objects or strongly regular graphs if you want. They are all pretty closely related to each other. So this is everything that I want to say about the low-dimensional regime. It is very interesting. It's understood reasonably well, to some extent in the same way as this Gerzon bound is understood well. And what I want to focus about is what happens for kind of higher dimension, although we will eventually kind of actually bridge the gap and say something what happens, kind of how these two regimes connect as well. So the first to kind of concretely, from the combinatorial point of view, study the high dimensional case. Lemons and Seidel already look into it for some specific cases, was Boris Buch in about 10 years ago. And really, he deserves a lot of credit here, I think, for realizing that certain extremal combinatorics ideas are useful, namely some Ramsey theoretic ideas in attacking this problem. And what he proved is that if you fix the angle and take dimension to be large enough, the answer becomes linear again. And really kind of the main content here is 1 over an odd integer, because the Neumann already proved that for all the other angles. But these are the kind of actually interesting kind of local spikes which we are actually looking. So then in that same paper, he posed a very, very nice conjecture, which is based on some constructions that I'm going to tell you how they look in the graph theoretic world a little bit later. I'm not going to explain them in the geometric world, but you can think how they translate back if you want. But what they suggest is that the answer might be, if alpha is 1 over an odd integer, that precisely the answer should be equal to r minus 1 plus r minus 1 over k minus 1. So this r minus 1 over k minus 1, if you don't care about this exact answer here, you should think of it as just saying 2r times alpha. That's roughly what it is, because kind of k is equal to 1 over 2 alpha. So if you plug it in here, then you get 2 alpha r, and you'll be seeing this 2 alpha r showing up a bit later. But really the kind of intuition here is this r is the kind of lower bound that we discussed a little bit before, and this is kind of how much beyond that you can go. And also this, in some sense, this conjecture is saying should be quite small, depending on exactly what the angle is. Very good. So then the next remarkable paper in the whole series of them was due to Bala, Drexler, Kivash, and Sudakov. So they proved that from the exponential regime, so once the dimension becomes exponential in at least 1 over alpha squared, you actually get an upper bound of 2r minus 2. So this is the first thing that really actually beat this Neumann bound. And also it's the best you can do if you don't have any extra information about the angle, because if alpha is 1/3 and you plug that into this conjecture of Boris, you get 2r minus 2. So this actually confirms Boris's conjecture for k equals to 2 or alpha equals to 1/3. And there are these tight constructions that I promise I'll show you in some form later. So you can't kind of beat this 2r minus 2 in general, but they also show that you can, if alpha is not 1/3, prove something like 1.93 times r or something of this flavor. So you do get something a bit better than that. Also, they kind of bring various other nice ideas to the table, which are kind of all subsequent papers are also using. So also some Ramsey theoretic ideas and various things that I'll show you later originate either from this paper or from the one from Boris. So I'll show you a bunch of arguments and kind of where this stuff is coming from. And this is a concatenation more or less of ideas that kind of matured and developed from all of these papers over the years. So the next really, really nice paper in the series is due to Yang, Tidor, Yao, Zhang, and Zhao, who actually proved this conjecture of Boris in full, which is quite remarkable and spectacular, I think, given that like it's actually an exact answer to this problem without any sort of asymptotics. except that they need the dimension to be at least double exponential in 1 over alpha squared. So again, I'm stating it here in 1 over an odd integer. They have a version that applies for every angle, but things become a little bit more complicated and depend on certain spectral graph theoretic parameters that I don't want to introduce. So as I said, I'm mostly sticking to 1 over an odd integer. So of course, kind of when we see this type of bound, we kind of get greedy and we want to improve this double exponential requirement. And also, if you read the paper, it really looks in various places that they're being very, very wasteful, and this should certainly be improvable. So kind of the more I'm giving this talk, the more people tell me that they have given this a go and kind of got nowhere. I'm also hoping to kind of explain a little bit later why that is the case, because there is a certain kind of big barrier that's sort of showing up at this double exponential, and that you sort of need to break if you want to get better bound, better kind of requirement on the dimension or improve the double exponential. So one actual success story in between, before our work, was done in this paper of Igor that I already mentioned on the previous slide. So he managed to improve this 1 over alpha squared in the exponent to roughly 1 over alpha. So there is this log 1 over alpha if you move it up there. But really kind of the more interesting feature of this result, I think, is that he removed one of the two major bottlenecks in improving this double exponential upper bound, lower bound on the dimension. And also because of that, he started getting some nice results also below this double exponential regime. So here it's not exact answer, but it's at least some reasonable bounds that actually go down both to exponential and even just the polynomial regime, at which point he got this very nice exact answers, sort of exact answers from the previous slide. So the point is that the Yang, Tidor, Yao, Zhang, and Zhao, as soon as you go just a bit below this double exponential, they give you a trivial bound. They give you nothing. And also you'll see in a moment kind of why that is happening and what sort of bound and kind of where this improvement of Igor really came into play. But for now, kind of to summarize the story, we kind of understand the answer up to double exponential regime, let's say up to a constant factor of not too big constant factor around 2. And after double exponential, we sort of understand it exactly. And the story is kind of, it jumps here around 1 over alpha squared, goes briefly to quadratic, and it's linear everywhere else. Very good. So the first result I want to mention is that we finally managed to improve this double exponential requirement in the result of Yang, Yao, Tidor, Zhang, and Zhao. And so we managed to improve it to just an exponential requirement. And so we get this exact behavior already when the dimension becomes exponential in some small polynomial in 1 over alpha. And also this is actually a special case of a general result that applies for any angle. So the top one is stated in this 1 over an odd integer form, but the bottom one is what happens for arbitrary angle. And here you see this r times 2 alpha, and that I mentioned is a kind of good thing to keep in mind for most of the talk because it's going to be showing up in a few places. So also, if alpha is not 1 over an odd integer, we can prove a better bound than what is written here, which really shows that kind of from this exponential regime, this 1 over odd integers are sort of local maxima in some sense. So you actually get provably that they are spikes that I was sort of waving in my hands before about. Very good. So the second result that we have is an asymptotic solution from the super polynomial regime. So we show that the answer is r plus little of r, assuming that r grows faster than any polynomial, and also that there is a kind of silly condition, but necessary in some sense, that alpha is small. And of course, this is necessary because if alpha was 1/3, then the answer here is 2r minus 2, I said, and there are constructions that show this. So you do need this 1 over alpha condition here in some form. So what this is really saying is that this little of r function here is hiding some sort of function of the form r times alpha, where kind of when alpha is treated as small, this is a lower order term. and also modulo certain kind of nice algebraic or spectral graph theoretic condition, namely that there is no graph with maximum eigenvalue equal to 1 minus alpha over 2 alpha, you can actually delete this requirement, and it's universally true that you get r plus little of r, where this is going to be something of the form r over log r, if I remember correctly. But we're also going to see something of that form later. So also I should say here, so somehow there is free asymptotics showing up in this statement, and I'm just putting it that way just to kind of keep it a bit cleaner and kind of give you the kind of the gist of the result. But from the spectral graph theoretic result, you hopefully understand what's actually happening in terms of the asymptotics. But just to say that this also, even when r is just a polynomial, say 1 over alpha to the 20, we get the best known kind of linear bounds that exist here. And it's just that somehow the better the lower bound you have on r, the better the constant that we get in front of r will get. And kind of the bigger that bound gets, the constant will tend to 1 for us. So this is sort of what's happening in the asymptotic secretly there, modulo this bit about alpha actually being a certain restriction showing up here as well.
Can I ask a quick question about this last theorem?
About
the last, the third theorem. So again, so if let's say alpha is, well, 5 or I know 7, then and let's say there is no graph with this maximum eigenvalue, whatever it should be, then your theorem holds for like asymptotically for r, or how should I
there
read
is
the
a
first
thing
condition?
that is kind of, so the thing is that if alpha is 1 over an odd integer, then there will always exist such a graph.
There will always, okay, so if let's say
and because this 1 minus alpha over 2 alpha being an integer is equivalent to alpha being 1 over an odd integer. So you'll see this kind of showing up a little bit later. So actually a clique is a graph that does that for you. This is actually where the constructions are coming from. So I'll get back to that in a moment,
okay,
but it's a very good question. It's just sort of hidden at the moment here. And also kind of, if you look at Boris's conjecture, kind of if alpha is 1 over 5, then the answer here is something like 3 halves r. And there are tight constructions for 3 halves r. So somehow like you will not be able to, for 1 over do that.
But if, okay, so let's say if it's not an odd integer, 1 over 6 or 1 over 5.5, then the first condition, the condition on r just says that for large enough r, we prove that it's r plus little o of r, right?
So the thing is, the first question to answer is, does there exist a graph with maximum eigenvalue equal to whatever that function is if you plug in 1 over 6? If it exists, it will give you a construction which evidences that the answer cannot be r plus little of r. And if it does not exist, then the answer is r plus little of r with I mean, so with upper bound at least being something like r plus r over log to some power, but we'll see that in a moment also. So as soon as they don't exist, you get this sort of bound, and if they do exist, then the answer is actually bigger than. But then again, kind of if alpha is getting larger, there is a certain term here which you can write also in terms of alpha. So it's I'm thinking kind of alpha. If you think of alpha as also being small, then that means. It's also kind of the second term here is really a lower order term compared to the first one. So the answer should end up getting closer and closer to r, and this is showing that this is indeed happening in some sense. Whereas before it was like an explicit 2r was the best upper bound that did not really improve or do anything better as alpha got small or did anything else in particular. But thanks for the very good questions. And also, please, everyone, feel free to ask.
Yeah, thanks, Matija.
Very good. So maybe to summarize, so the situation now is we sort of understand the answer up to a constant factor when alpha is, when the dimension is polynomial in 1 over alpha. We understand it up to lower order terms when it is a super polynomial, and we understand it exactly when it's exponential or super exponential. So that's sort of the new story about this function. Very good. So let me now try to explain how what this has to do with spectral graph theory and why there is this curious condition of a graph with maximum eigenvalue showing up. And then tell you what is the story in the second problem that I want to talk about, and then also kind of tell you how we are proving some of these things. So the setup is we have n lines, which any pair of them define the same angle. We translate them so that they go through the origin, and we are in r dimensions. And our goal here is to show that n isn't much larger than r. Right? That's the sort of bounds that were showing up on the previous slides. So let's put unit vectors on each of these lines so that we get rid of the geometry and start talking about algebra. So here I want to put them to be of unit length, and know that you actually have two choices on each line. For now, I'm just going to pick an arbitrary choice, but it's going to be important in a moment. And let's write down what we know about these unit vectors from the setup of our problem. So angles always translate to information about dot products in geometrical algebra. That's actually how the angle is defined in higher dimensions. And this is precisely, as Andrei observed a bit before, why I picked that arc cosine normalization a bit before, so that actually, like the angle being arc cosine alpha, tells you that the dot product between these unit vectors is equal to alpha or minus alpha. And for me, alpha is just chosen to be positive just for convenience, but it can be either plus alpha or minus alpha, depending whether in the how you picked your unit vectors, they close the small or the big angle, as we discussed before. And also because we're picking them to be unit vectors, the dot product with itself is 1, so we get all the information about the dot products. And these kind of dot products make a matrix, which is called the Gram matrix of these vectors, which has some nice properties, namely it's positive semi-definite, and also it's a product of two low-rank matrices. Namely, this is an n by n matrix, right? So there are n vectors here, and so this is n by n dot products that we are encoding in this matrix. But actually, you can write it as just a product of an n by r times r by n matrix, in which kind of the rows of the first one are just the vectors, and the columns of the second one are exactly our r-dimensional vectors. And you get as the entries the dot products. But the point here is that this is an n by n matrix which has rank at most r, because it's a product of an n by r matrix which has rank at most r. And remember, our goal is to show that n isn't much bigger than r. So if n is assumed to be much bigger than r, then this is a lot of information that we want to exploit from this matrix. Very good. So we have this matrix. So one thing that we don't understand about it is what's happening with the plus and minus alpha. So let's introduce some auxiliary graph G that is going to encode when we get a negative dot product. So this is a graph whose vertex set are the lines, and we put an edge between any two lines which give you a negative dot product. So if you think a little bit about it, like negative dot products, there shouldn't be too many of them. And this is actually where these Ramsey theoretic ideas came into play. And actually, one of the very important lemmas that we are going to use that Igor proved in his paper is that if you make careful choices of the signs of your unit vectors, you can actually get a pretty good upper bound on the maximum degree of this auxiliary graph. Namely, you can bound it by 1 over alpha squared. And actually, his function here is less pretty and much more exact because he wants to be able to get tight bounds depending on this existence of strongly regular graphs. But for us, we're like a less precise bound is perfectly fine. And actually, in our paper, we give a kind of simpler proof using Cauchy-Schwarz, which gives 1 over alpha to the 4. So, and that's also essentially just good enough for us as 1 over alpha squared. So in his paper, this is a much more substantial proof because, again, he needs to keep things tight and he is using certain projection inequalities in Frobenius inner product space. It's a very, very nice proof. but we don't quite need that much power. And actually, from one lemma that I'll show you later, you can even bootstrap our 1 over alpha to the 4 bound into a 1 over alpha squared one. So you'll see that hopefully a bit towards the end of the talk. So just again to summarize this auxiliary graph G, it's encoding where we see the negative dot products. And what we can ensure is that it's sparse, so it has a small maximum degree. Small meaning upper bounded by 1 over alpha squared, just to keep things clean. I'm not going to show you a proof of this lemma because it's a bit of a digression and from where I want to go. And it's also really a result from the previous paper that Igor proved. But this is one of the, I think, few things that in the reduction I'm not going to show. Very good. So now let's write down this equation here. So this definition of the Gram matrix in some sense as a matrix equation. So in particular, I want to write M in terms of the adjacency matrix of our auxiliary graph. So A here is the adjacency matrix of graph G, J is the all ones matrix, and I is the identity. So what I'm doing here is I'm saying, well, this Gram matrix, let's start with making it being alpha everywhere. And then where we want to have a minus alpha, let's just take a -2 alpha. This is what the adjacency matrix is encoding. And then we remember that we also need to fix what's happening on the diagonal to get 1 there. So the adjacency matrix has nothing on the diagonal. All ones has alpha, so we need to add 1 minus alpha times identity to make it all ones. So there is nothing really interesting happening here. It's just writing this definition in terms as a sort of matrix equation. And also, if you've ever seen these strongly regular graphs or like Hoffman-Singleton theorem proved, this type of expression might seem familiar. And this is really where this sort of connection to these objects is kind of hidden. This is secretly coming. Very good. So now what are we going to do with this strange matrix expression? So first, we're going to remember this low rank intuition that I mentioned before. Namely, M is supposed to be a low-rank matrix, and we have another low-rank matrix on the right, namely the all-ones matrix. So let's put all the low-rank stuff on one side, and this is like now a nicely commuting pair of matrices on the right as well, which is going to be convenient. And let's now actually use the subadditivity of rank. So namely, the left side is still of low rank, so it's at most the rank of M plus the rank of all ones, which is 1. And as we said, this is the Gram matrix of R-dimensional vectors. So its rank is at most R. It's a product of an N by R by an R by N matrix. So it's of low rank. And then since we are kind of interested in like the difference between N and R, it's also quite natural now to just use the rank nullity theorem to switch into nullity and say that, well, this tells us that nullity of this matrix should be huge if N is much bigger than R, right? So we should have a very, very, very big kernel. Very good, but now kind of we don't understand anything about this M minus alpha J matrix. It's sort of arbitrary, but the matrix on the right is essentially an adjacency matrix of a graph, which is slightly like translated and modified by identity, which means we kind of can keep track of what's really happening. So what this is saying is that actually the nullity of this 1 minus alpha identity minus 2 alpha times the adjacency matrix is large. And this is just the multiplicity of 1 minus alpha over 2 alpha as an eigenvalue of this adjacency matrix, or equivalently of our graph G. So this is where that kind of hidden 1 minus alpha over 2 alpha was showing up on the previous slide. So that's exactly that function. And here again, I'm just using that identity and A commute very nicely, and that you can always divide nullity by non-zero numbers and so on. So I'm also tacitly assuming that alpha is not 0, because that makes them orthogonal, and we understand everything in that case. Very good. So to summarize, what we just proved is that the maximum number of equiangular lines in R dimensions is upper bounded by the multiplicity of 1 minus alpha over 2 alpha as an adjacency of this auxiliary graph G, of adjacency matrix of this auxiliary graph G, plus r plus 1. And remember, our goal here is to show that this isn't much bigger than r. So really, we want to show that this multiplicity is not too large. And also, the thing that we can ensure, which is kind of crucial for us, is that this graph isn't too dense. So we get this, this upper bound on the maximum degree that is going to be very useful later on. Very good. So let me now clean up this slide and just keep what I'm still going to need. So we proved this upper bound on the number of equiangular lines in terms of the multiplicity of this as an eigenvalue. And I'm still going to need the positive semi-definiteness of the ground matrix for just one more line. So let it stay here. And the only other stuff that I care about is that this is an n-vertex graph with upper bound on the maximum degree. Now, there are the first question that one asks when you see this is, well, there are a few cases depending on which eigenvalue this 1 minus alpha over 2 alpha will be. If it is the largest eigenvalue of G, then this is relatively easy to solve because somehow we understand the largest eigenvalue very well. The maximum is just the number of connected components that the graph has, which have this as their largest eigenvalue. And in order for a graph to have this as its largest eigenvalue, it needs to have at least this plus 1 many vertices. Right? So if it's a clique on that many vertices, it will have that as an eigenvalue because it's equal to the max degree, and it's very easy to show that it will always be smaller otherwise. So what that means is that in this case, we know what the answer is. It's going to be n over lambda 1 plus 1, assuming lambda 1 is an integer, so that we can actually build this clique. And then it is actually the answer because we can just take this joint union of cliques of that size and we actually get that many eigenvalues that are equal to that. And this is precisely this construction that Boris used. Well, it wasn't presented in that form, but if you look at the geometric one, it really is just clusters of lines that kind of build you these cliques in terms of the inner products. So once you have this, you can actually go back and build a construction of, it's not completely obvious, but you can do it in the geometric world as well. And this is exactly where this Boris's conjecture is coming from and those expressions that you saw before. If you plug in, instead of this expression on the right here, 1 minus alpha over 2 alpha plus, n over 1 minus alpha over 2 alpha plus 1, so n over lambda 1 plus 1, and you shuffle stuff left and right and whatever, you'll get precisely the bounds that we saw before, except I'm lying to you by 2, because this plus 1 should be a minus 1. And in this case, you actually, if you go back to the previous slide, you can use this better version of this subadditivity of rank inequality to get r minus 1 here. And here it's important so that you actually get tight bounds, otherwise you would be off by 2. But in the second case, I actually don't know how to do it, but luckily it will not be important. And what is the second case? Well, we now kind of resolved what happens if it's the largest eigenvalue. Now, what if it's the second largest eigenvalue? Well, this is still something we have some sort of idea about. And if you're familiar a bit with spectral graph theory or theory of expander graphs and so on, we sort of understand a bit about the second eigenvalue, but it's a much more difficult parameter to understand than the first one. So here, I think it would be kind of notoriously difficult to get exact answers in this case. But the silver lining is that we actually don't need to find exact answer in the second case, so long as we can prove a bound which is better than whatever we get from the first case. Right? So in the first case, we have constructions that tell you can't do better than this. So I don't need a perfect understanding in the second case. I only need a bound that beats the first. And this is really secretly the reason why we can get these exact answers in this problem, because somehow like this is, I think, extremely hard if you want to understand exactly what the answer will be. But understanding it, but proving a decent bound is a much more reasonable requirement. It's still very interesting and highly non-trivial, as you'll see, but much more manageable. So this is what we'll be focusing on. So really kind of I will be assuming that this 1 minus alpha over 2 alpha is the second largest eigenvalue. And for that to really be fine, I also need to deal with the third, fourth, fifth, and up to nth case. But actually, none of these can happen. And this is where this positive semi-definiteness of the Gram matrix comes into play. If this would be a third or lower eigenvalue, then you can take two eigenvectors of larger eigenvalues. You can take some sort of linear combination of them to make them orthogonal to the all ones vector, and then evaluate the quadratic form defined by this Gram matrix here, and you'll get something negative, which is a contradiction to positive semi-definite. Again, it's like a few lines of algebra that I don't really want to do, but what it tells you is that you can assume that this 1 minus alpha over 2 alpha is precisely the second eigenvalue. It's also actually for most of the argument not going, it would go through pretty much the same if you assume it's whichever eigenvalue below second you wish, but it's cleaner to think about it as a second.
Matija, so just to check that I understood correctly, so you're saying if it's like the third eigenvalue, then just the matrix above cannot be positive semi-definite, right?
Yes. So you get a contradiction to that by like, so because you will find a vector so that like if you multiply this matrix on both sides,
then it evaluates to negative
you'll
number.
get something negative. And this is because you pick it orthogonal to all ones so that this eventually disappears. And then you're evaluating 1 minus alpha over essentially, so you'll just get precisely that. Again,
I understand. I see the proof now. Yeah, okay.
So I mean, it requires writing out, but it's not such a crucial thing. So I did not want to go into it too much. But it's also not a complicated thing. So a similar type of argument also allows you to assume that G is connected in the second case. So again, if you have two connected components, you can take two eigenvectors and then play some games. So here, instead of positive semi-definiteness, you would use the variational definition and to be a little bit careful. You also can just go and sort of solve the problem on the connected case and then patch together the solutions. But it's again cleaner to just assume it's connected. And it is actually crucial in a few places, but there is various ways to get around this, and it's not something very difficult. Very good. So to summarize, what we have now is an n-vertex connected graph with some control on the maximum degree, and we know what its second eigenvalue is. It's this 1 minus alpha over 2 alpha, and the max degree is at most 1 over alpha squared. But really, this I'm now stating as a completely general problem. I give you an n-vertex graph. I tell you what the max degree is. I tell you what the second eigenvalue is. And I'm asking you to give me an upper bound on the second eigenvalue multiplicity of this graph, which I think is actually a very, very nice and appealing question in spectral graph theory in its own right. And this is precisely what Yang, Tidor, Yao, Zhang, and Zhao used, and they prove such a result. And this is where their result in the equiangular lines is coming from. So the type of bound that they proved here is of the form n times log max degree divided by log n. So if we stare at this for a moment, you'll realize that actually this gives you nothing unless the maximum degree is smaller than a small polylog of n. And the reason is that if this log delta in the denominator is bigger than the log n in the denominator, then you just get a bound that is worse than n here. And n is always a trivial bound on the second eigenvalue multiplicity. So this gives you absolutely nothing in that case. And also because they had these Ramsey theoretic ideas to give them control on the delta, their bound was actually exponential in 1 over alpha here. So with this log, this is one place where the double exponential was coming from. And this is precisely the one that Igor removed because he could improve the delta upper bound to 1 over alpha squared. So he reduced this one to just exponential. But the second part of the story here is that if you want to get exact answers, then you actually want this log delta over log n to be smaller than 2 alpha, roughly speaking. A bit better than 2 alpha, but this is what comes from the previous bounds. Again, up to some reshuffling of the bounds. We can go back to the previous slide to see the exact statement. But what it translates to is that this log n divided by log delta should be bigger than 1 over alpha, which is again a double exponential requirement. And this is the one that was not removed before our work. And also here you have this log delta moving now to the right. So with Igor's bound on like polynomial, he got 1 over alpha times log 1 over alpha, whereas Yang, Yao, Tidor, Zhang, and Zhao were getting 1 over alpha squared on the right because they had something exponential in the place of delta, so they get another 1 over alpha on the right. And again, what is really happening here is if we go back to this bound here, so this inequality that we're getting, so the trivial bound on the right here is n, which gives you nothing. So you conclude nothing. And also, if you prove a bound that is of the form something like n over 2 here on the multiplicity, you get a bound which is of the form n is at most 2r, which is in secretly where all of these 2r style bounds were coming from before. But if you want to get this r plus alpha r times bound, what you really want here is something of the form 2 alpha times n. And really kind of the way to think about it is that in that setting, you already get a bound which makes n and r pretty close to each other. So whether it's n on r here doesn't really matter. It's just lower order terms. Of course, you need, like if you want exact answers, you need to be much more careful about this. But let's say I don't, for this talk, go into constant factor additive terms that you do need to be careful about if you want exact answers. Very good. So this is sort of where these two kind of bottlenecks on the, at least numerically, were coming from. And if you look at the proof of this result, as I mentioned before, it really looks like it's wasteful in a few places, and it feels like you really should be able to do better. But then kind of lots of people tried and failed. I tried about 3 times, I think, over 5-6 last years. And kind of then came a paper that sort of explained why we sort of all failed for a while. And the reason is that there are actually connected graphs which do have n over log n eigenvalues, which are very close to lambda 2. Now, these are not showing that this is a tight upper bound because they can't get them to be exactly lambda 2. But for all of the upper bound arguments that we have, they're all of analytic flavor. So they can't really distinguish between lambda 2 and something which is very close to lambda 2. So somehow this explains that really, like, you need to do something that's a bit different than analytic if you want to get a kind of universal improvement here, which is still open and very, very possible. So what we did is kind of took a step back and proved a sort of bound which goes in a different direction. So it's a bound that kind of, depending on the regime, does better or worse than what is written on above. But in particular, it's in terms of this value of the second eigenvalue instead in terms of the maximum degree. So what we prove is under this same assumption that they sort of implicitly had in the above theorem, that the maximum degree is at most a small polylog, which is actually the main place where our kind of this exponential requirement still exists for us. Then we prove an upper bound of n over lambda 2 plus 1. And this is sort of motivated a bit by this first case. So we're really just trying to prove precisely the bound that you need to beat the first case when it's the largest eigenvalue. So if you ignore the second versus first eigenvalue here, this is actually tight, because if your graph is a disjoint union of cliques on lambda 2 plus 1 vertices, then the second eigenvalue is equal to the first, and the multiplicity is n over lambda 2 plus 1. Of course, if it's the second one, then it's plausible that you can do better than what is written here, except if the degree is too high. I will get back to that in concluding remarks and some open problems later. But realistically, this is essentially kind of the best you can hope to prove in general, unless you kind of start adding extra assumptions on your graph G, which in our problem we do have and we do want to use, and we do have to use, because we really need here something like this minus 3 on the right-hand side in order to get these exact answers, because we need to beat that loss of plus 2 and a few other kind of things where we'll actually lose a bit. But what we can do is actually prove a somewhat stronger version of this result, which kind of says that if you know something about the expansion of your graph, you can improve this bound. And then actually just using the connectivity assumption as a sort of weakest possible expansion assumption that you can get suffices to get this extra tiny constant improvement that we need.
Sorry, I have a question.
Yes, yes.
We have some special graph with scalar products equals minus alpha. And as I see, in all these claims, we use only bound for the maximal degree. Am I right?
You are right. And also kind of the second eigenvalue is something specific in terms of that upper. So technically, it's only the upper bound on the max degree in terms of the second eigenvalue. Right? Because the second eigenvalue is for us 1 minus alpha over 2 alpha there, which is roughly 1 over alpha, think of it that way. And delta is upper bounded by 1 over alpha squared. So these are sort of the only things that feature. So this statement here is not about that special graph. This is a general universal graph statement that we just apply to that specific graph. And you are absolutely correct that it's more than plausible that you can extract extra information from that geometric graph, which might help you to prove these bounds, either give like easier proofs or actually let you prove things easier. I mean, prove kind of better bounds here than what's happening.
Yeah, so in some cases we cannot have the example with the cliques. Just
yes,
clicks.
Precisely. So this is again this business of when it's 1 over an odd integer or it's not 1 over an odd integer, because like this kind of, if it's not 1 over an odd integer, then you can't use cliques. If it is, then you can use cliques. And if it's something else, then what you're really chasing is the kind of the smallest graph which has largest eigenvalue precisely equal to this 1 minus alpha over 2 alpha. And this is a reasonably well studied and reasonably completely not understood parameter in spectral graph theory, but it sort of confuses things a lot. So as I said, I'm like in terms of the equiangular lines problem, I'm always tacitly assuming we are in the world the 1 over an odd integer being the angle. So that's the sort of case that happens here. In general, I agree with you. What happens kind of in between is also, again, an interesting question, and you will be able to do much better than this bound if lambda 2 has certain algebraic properties, etc. So it's not like universally tight for any choice of lambda 2, but unless you know something about it, this n over lambda 2 plus 1 is sort of the correct thing that you should be aiming for. Unless, again, so we are exploiting that it's the second eigenvalue, and strictly smaller than first. We are exploiting connectivity in some places, etc. So a few other things do kind of come into getting these exact bounds, or like, well, beating that bound. But this theorem, as stated, it's like it doesn't assume anything on the G. Well, I think I'm maybe tacitly assuming connectivity because you get some silly type of things when you build two graphs. Let me not go into that. But yeah, technically I'm assuming it's an n-vertex connected graph, and that's the only thing that I'm assuming for this theorem, and everything else later on. If it's not connected, it's kind of this multiplicity questions. You just go at every connected component and you analyze that. But yeah, very good. Thanks for the questions. Any other questions? Okay, good. So now, this theorem talks about sparse regime, right? So I'm assuming that maximum degree is a small polylog. And actually and this is the theorem that kind of translates to our new, like from exponential regime exact result in the Equiangular lines. But for our second result there, which was telling you what happens in the kind of sub-exponential regime there, actually what's happening is you need to understand what's happening in this problem when your graph is possibly a bit denser than this. So I refer to this as a kind of dense regime in the eigenvalue multiplicity problem. And here, essentially and practically nothing was known before that applies for all graphs. So you can extract from Igor's paper, if you kind of add some of our ideas as well, a bound of n over 2 on the multiplicity. So that kind of just beats the trivial bound by a factor of a half. And this is where these sort of 2R bounds were coming for him, as I kind of explained a few slides ago. And the only kind of general result in this flavor that was known is due to Mackenzie, Rasmussen, and Srivastava, which, however, had like a certain extra restriction, which is that they needed the graph to be regular. And then they could prove a bound of the form n over roughly log n, where there is some nasty parameters of log delta floating around. And I don't encourage you to kind of try to decipher the logs, that they will not be so important here. But if you do that, you'll notice that this is again becomes a trivial bound if the maximum degree is smaller than something like 2 to the root log n. So this result, again, doesn't really apply all the way to the polynomial regime. It still has an upper bound on the max degree, but it is better than assuming that the max degree is smaller than a polylog. So this is kind of quasi-polynomial in substance. But regularity here is a much bigger issue for us because these auxiliary geometric graphs, we don't know how to make them regular. They might be, don't really see why they would be or wouldn't be, but we don't know how to do that. You can't even use this result directly, and it doesn't really cover the whole range. So also here I should mention that they do give graphs, which again, similarly as in the previous slide, show that this n over log delta n is roughly the correct behavior here, if you're interested in kind of a small interval around lambda 2 instead of just lambda 2. So here what we prove is a stronger bound, which doesn't need regularity, and that applies for the whole range. So here I stated it in the form that we assume that lambda 2 is bigger than this log delta n. In reality, like lambda 2 and delta are sort of tied to us, and we can even tie them for the purpose of this theorem. But this choice of lambda 2 lower bound just kind of ties in the two theorems that I told you, because the other one is roughly n over lambda 2, and this one is roughly n over log delta n. So this kind of gives you a sort of smooth transition between the two theorems. But this is precisely the theorem that allows us to get this up to lower order terms result in the equiangular lines world. And this is also where which explains this super polynomial requirement there. So here, if n is, so delta, remember, is something like 1 over alpha squared for us. So if n is polynomial in 1 over alpha, then this log delta n term is just a constant. So you're getting a bound which is n over a constant, so it's not a little of n bound which we would need for lower order terms. But also if it's n is kind of a big constant in 1 over alpha, then you do get a big constant here, so you do get better and better bounds. So really this is the thing that you should plug into there. And here the little of one is not scary at all. It's some log term of the same form as this log delta n. So I just put it inside here to not to make it a cleaner state. Very good. So these are the kind of two of our main results in the spectral graph theory side of the story, and kind of the proofs of the two results, which I want to tell you a little bit about in the remaining time. They're actually somewhat different. So they use this common framework that some of which I told you about, some of the new ideas that we also bring to the table. But realistically, the core of the idea for the proof of this theorem is using some probabilistic ideas, whereas the previous result from the one from the previous slide is using some more structured kind of ideas. And in both cases, what I mean really is we are using this Cauchy interlacing theorem, if you've ever seen it. If you're not, don't worry, I'll tell you what consequence of it we want to use and in a moment. But really what it allows you to say is that if you delete a bunch of vertices from your graph, say k of them, then this decreases the multiplicity of any eigenvalue by at most k. So if you're familiar with it, this is it tells you when you delete a vertex, the eigenvalues should interlace. And if you do that multiple times, you will get this statement. So it's a corollary of Cauchy interlacing theorem. But really just remember for this talk, what we care about is this statement. If I delete k vertices, I decrease the multiplicity by at most k. And I'll refer to this as Cauchy interlacing theorem, just so that because I think of it that way. Very good. So when I say kind of we're using probabilistic ideas here, what I really mean is we're kind of going to delete a random set of vertices and apply Cauchy interlacing theorem, and then several other ideas on top of it, the trace method and various lemmas that I'm going to show you. And on the previous slide, what we're doing is we're deleting much more carefully vertices and kind of in a much more structured way. So for the rest of the talk, I'll actually focus on the theorem on the previous slide. So the n over lambda 2 plus 1 bound, because I think it's a more interesting kind of argument, and it involves one lemma, which I like a lot, and I think is potentially useful in other spectral graph theory problems as well. So let me start by kind of explaining two lemmas that are useful for us, and
Matija, can I quickly
Yes.
ask a question about the previous things?
Mhm.
So all this, I guess two questions. So one, so there are all these examples with eigenvalues close to lambda 2. So your proof still works with eigenvalues that are close to lambda 2, or it's for the exact kind of eigenvalues?
So it does work for this case. In this case, if you notice kind of what it's showing here, it's n over log delta n to the 3/2, which is not contradictory to that. And this one will go through with eigenvalues which are close to it. So there is one caveat. So I'm like, yes, it will go through, but you
And even for the example of the previous group of Jiang, Zhao, etc.
Second, sorry, I did not.
So on the previous, you also had I mean, you mentioned for the work of Jiang, Zhao, etc. There are examples with n over log n.
Yeah.
Still, it's not. I mean, it doesn't contradict your statement, right?
It doesn't contradict the statement, and in particular, kind of the thing is that these graphs have a certain specific kind of value of lambda 2. So somehow, like our bound is not in terms of n alone. Something, and also like the size of lambda 2 compared to log n is also like there is trade-offs, but it will beat log n kind of for the interesting regime for us. But once you get beyond that, it's like actually this result starts being stronger again. And we can actually, because this expansion thing that I mentioned allows us to kind of put together these two bounds and have a kind of universal stronger thing. But again, I just wanted to keep a cleaner state.
It's just a little bit like it's subtle, these differences. So
very much so. So we still are using analytic bounds in the terms of that we're using the trace method, and we still so there is actually one place in the proof where we are using now exactly lambda 2, but I do know how to get rid of that step if you want to get an completely analytic proof still. But still, that step is something that I think could actually be very useful, because it's it's actually this lemma one that's going to show up soon. But there is one more step. But yeah, so what I'm saying here is kind of that, like, we're not dealing with the kind of analyticness issue. What we're doing is really we kind of realize that you want bounds that depend on different parameters. And this is so kind of we change the story in some sense of what sort of actually trying to prove, rather than a universal one in terms of n, one that actually depends on the eigenvalue. So still, in some sense, if you want to go, so now I think it's much more pronounced, although there is still a little bit of stuff you can do without kind of without getting into these barriers that pop up because of these constructions. But now we are really kind of hitting badly these analytic versus non-analytic barriers. But it's a little bit too much of explaining the numerology to get to that. So let me rather show
of course
work some more kind of way handy high level way, and you'll maybe see it from the last slide, I hope. Very good, thank you. Right. So I want to show you two lemmas, and the first lemma is used in both theorems actually, and it's something that we can also replace with some other ideas and even with some arguments that existed before, but it makes things much, much cleaner, and it gives you, I feel, like a little bit of extra power that doesn't really feature super strongly in our current results, but still kind of you'll see kind of why it's nice and clean in the next slide. And it's also a very nice kind of observation, I think, that could be very useful in trying to proving things in the future or improving things in the future. So what it says is that if you have a host graph G and you have a subgraph H, which has its largest eigenvalue bigger than the second largest eigenvalue of the host graph, then you get an upper bound on the multiplicity of the second eigenvalue of the big graph, which is of the form how many vertices the small one has times the max degree plus 1. Okay, so why is that useful for us? Well, we're trying to prove bounds which are kind of at best of the form n over log n on the right here. So if you can find a small subgraph of our graph there, which has a large first eigenvalue, then you're done immediately. And the small means something like n over log squared or n over some small polylog, essentially. So that means that any small subgraph, and not very small, still n over log, that's huge in graph theoretical terms, needs to have, by this lemma, its eigenvalue at most lambda 2. Of course, this is not enough for this Cauchy interlacing business, because like that, you would need to still delete most of your graph to get to this size of the thing, but still it's giving you a lot of information and it's kind of very useful in several places. Now, this is a rather simple lemma once you decide to prove it, and so let me just sketch how the proof works. So what we'll do is look at this subgraph and expand it once. So you get at most delta times the number of vertices of H many extra vertices. So now the total number of reached vertices is precisely this right-hand side. And this is what we will Cauchy interlace view on. Essentially, we'll use it, we'll delete it, and then argue something about the rest. Because I'll kind of explain in a moment that the rest of the graph needs to have its largest eigenvalue strictly less than lambda 2. Once you have this, Cauchy interlace completes the proof of the lemma, because again, you just delete all of these vertices, you decrease the multiplicity by at most that, but it is now equal to 0 because there is no more eigenvalue equal to lambda 2. So it was not more than that to start with. Now, why is this inequality on the right true? Well, assume that it's at least lambda 2. Now, what you have in your graph is two subgraphs. One is this complement piece on the right, and one is H itself, which both have their largest eigenvalues bigger than lambda 2, okay, bigger or equal in the second case, and have no edges between them. So again, you can take the two eigenvectors of the Perron eigenvectors, the eigenvectors of the largest eigenvalues of these subgraphs. You can take some combination of them to make it orthogonal to the Perron eigenvector of the big graph. And then you will get a contradiction to this variational definition of lambda 2, if you've ever seen that. So this is a sort of definition of lambda 2 as this sort of min-max thing of over quadratic forms. If you haven't seen it too much, don't worry about it. It's a similar type of idea that I sort of explained a few slides ago when we were talking about connectivity and about like not being the third eigenvalue. And the crucial bit here is that there should be no edges between these two subgraphs, because that in the quadratic form means that you'll not get cross terms when you take the quadratic form. So this is why we need to delete these neighbors when doing this, and why we get the extra delta term showing up there.
So we only delete neighbors that are not inside H, right?
Yes. Mm-hmm. So we can also improve this bound a little bit, because you can H is connected. There is various things. So think maybe in the paper we have it without +1, but I think this like it's small stuff that only might eventually become important if you're really chasing for exact results on various things. Very good. So let me show you the second lemma, which is new, and I like it a lot, and it looks very scary because there's lots of terms showing up here. So let me again rather explain it in terms of a picture. It's actually something rather natural if you kind of see it in terms of the picture. So the type of problem that this lemma is dealing with is, suppose I give you a graph, and suppose I add one edge to that graph. How much does the largest eigenvalue grow? Right, so it's actually a very natural question. It's something that has been studied in spectral graph theory for a very long time, and it's something that they understand very, very well, actually. There is a theorem of Nikiforov, which tells you that how much it grows is it grows by roughly 1 over the largest eigenvalue to the power diameter of your graph. And this is tight. So it's tight because you can take sort of lollipop graph, which kind of has a click here and then a long path going below it. And then if you add an extra edge on bottom of the long path, how much it will increase the largest eigenvalue is roughly 1 over lambda 1 to the power diameter, which is essentially just the length of the stick of the lollipop. So what's happening here is this lemma actually proves a sort of conditional improvement over this Nikiforov bound. And it's crucial for us because you can use this Nikiforov bound to actually give a different proof of both the Yang, Yao, Tidor, Zhang, and Zhao result, and also the Mackenzie, Rasmussen, and Srivastava. So they didn't use this Nikiforov bound. They kind of reproved some version of it that they needed, but you can't just use it as a black box thing. And actually, this is like, if you just use that, you will get this double exponential requirement, and you'll, well, get some other issues in the Mackenzie, Rasmussen, and Srivastava problem. But namely, kind of controlling regularity there is what comes into play, but I don't want to get into that. I'm talking about the first problem only. So the problem is somehow that because this Nikiforov bound is tight, well, you can't get an improvement by kind of just directly improving the Nikiforov bound. So what we're doing instead is we're proving this conditional improvement. And what it's really saying is, let me decode it in terms of the picture, is that you go and you look at the boundary vertices of the small subgraph. And what do I mean by that? These are all the vertices that send at least one edge out of it. You delete them, and you get the leftover of the small graph. This is what's inside here. If you can tell me that this leftover has the largest eigenvalue being a little bit smaller than the largest eigenvalue of this subgraph, then actually you will get a much bigger increase than Nikiforov tells you when you grow from F to this bigger graph. It's a somewhat counterintuitive lemma when you see it the first time, but it's essentially kind of saying that the boundary vertices here, they are responsible for a decent amount of kind of the density or of the reason why the largest eigenvalue of F is large. So that means they're not kind of irrelevant as in this lollipop example, so that when you kind of add something to it, you get zero impact on, well, very little impact on the largest eigenvalue. And what's happening in our result is we're getting an increase, which is 1 over lambda 1 to an absolute constant, namely something like 2 or 4 if you take the roots in this inequality, instead of diameter showing up. And this is really the crucial step in which kind of the double exponential will go to a single exponential for us. So if you use this inequality with the diameter bound, this Nikiforov tells you immediately, you will get a double exponential bound. A requirement, sorry, on the dimension before.
Sorry, so for this lollipop example, so in this sense, K would be, or like F would be everything but like the bottom vertex of the lollipop or something?
Yes.
Uh-huh.
And then the boundary is just a single vertex, and this one. So so here, kind of, this will not satisfy the requirement we have here by a mile, and it should not, because actually it's not true for it, what I'm writing here. Like a much weaker increase is what you get. But you can actually recover Nikiforov. So we have a kind of more general version of this lemma, which applies for any graph you want, which recovers Nikiforov as well. So what it does is, instead of just deleting the first boundary, you can go and you can delete the second boundary. And then you get 4s here instead of 2s. So it becomes a weaker statement, but you only need to tell me something weaker about your subgraph. And if you delete the third neighborhood, then you can do a 6 here and so on. So you keep deleting boundaries or neighborhoods of the complement if you want, up until you decrease the largest eigenvalue of this small thing by something tiny, not much, but just some noticeable thing. And at that point, you get the increase, which is 1 over lambda 1 to the power of how many boundaries you killed. And in that way, of course, if you do this diameter many times, you will eat the whole graph and you will ensure this, and you get Nikiforov bound back. So it's a kind of general improvement to Nikiforov that does kind of, if you have some nice information about your graph, it does much better. So the proof here is, I'll not get into it. It's like 1 page. Once you decide this is what you want to prove, it's not so difficult. It's, again, using some clever Cauchy-Schwarz and carefully chosen pair on eigenvectors, and also a bit of the trace method to exploit this boundary property and kind of gain a little bit in this variational definitions of eigenvalues. So it's a nice kind of combination of algebraic ideas. It's not very complicated thing. It's, I think, kind of the main gist here is to really understand what you're trying to prove, and kind of also that this is something that you can actually ensure in the problem that we're looking at, so that it's actually useful. Very good. So this is the final thing that I want to show you. So as a proof sketch kind of this n over lambda 2 plus 1 bound, I'll actually prove something slightly weaker just so the numbers look nicer. And also, but it kind of illustrates how the proof works in general, and I'll be sloppy in a few places, but I think it kind of, the high level is what I'm trying to show you. So the setting is, again, we have an n vertex graph. You can, for this thing, we don't really need to assume connectivity, but you can if you want. We know lambda 2, we know delta, and we are trying to prove an upper bound on the second eigenvalue multiplicity of roughly n over lambda 2 plus 1. Now, the first kind of key idea is what we are going to delete for our final Cauchy interlace. And this is going to be centers of some stars. So what we'll take is maximal vertex disjoint collection of stars of size lambda 2. So each of them has lambda 2 plus 1 vertices. So in total, this is at most n over lambda 2 plus 1 stars. And what we are going to do eventually is delete their centers. So this is precisely what we can afford. So I'm going to show you that whatever is left will have a tiny second eigenvalue multiplicity, or tiny of lambda 2. And so combining this with deleting the centers, you will get a kind of bound that is very, very close to n over lambda 2 plus 1. And then you kind of introduce this expansion and some other kind of ideas to try to actually boost it down under n over lambda 2 plus 1. But I'm not going to talk about that. Very good. So far the story is we have a bunch of vertex disjoint stars, and we deleted their centers, let's say, and the leftover graph I'm going to call H. The original is G. So these are sort of going to be the graphs we are going to apply this Nikiforov lemma eventually. So the game here is I want to delete a bunch of vertices to kind of ensure that when you kind of do something that is going to happen in a moment, you can boost the size of the largest eigenvalue through that lemma that I showed you before. But let me go one step at a time. So the next and kind of the key kind of general method we're using is the so-called trace method, which means that the sum of the eigenvalues is equal to the trace of a matrix. And also, if you take the powers of the eigenvalues, then they are equal, sum of the powers of the eigenvalues is equal to the trace of the same power of the adjacency matrix. So here I'm ignoring most of the values and insisting that we take an even power so that I don't need to care about positive and negative ones. And I only care about the lambda 2 ones. So we have multiplicity, many of them. Each is lambda 2 to the 2k, and this is upper bounded by the trace, which is just the sum of all the eigenvalues that show up. Okay, so nothing scary happening here. So the next step is that, well, you can write this trace also as just the sum of diagonal entries of your matrix, which is just algebraically, you can write it as a kind of this like form version, or if you want, quadratic form version with the standard basis vectors. So this is just a convenient way of writing the diagonal entry of AH corresponding to vertex V. And now combinatorially, we understand diagonal entries, what they are and what they mean. Namely, they just correspond to the number of closed walks that started at vertex and that have length 2k. Right, so this is one of the basic lemmas that if you've ever seen some spectral graph theory before, that is usually shown. And it's very easily proved by induction if you haven't seen. Very good. So now one easy observation is that that means that in terms of kind of counting these closed walks, I only care about the ball around that vertex of radius k, right? Because if I'm counting closed walks of length 2k, they can't reach farther than k from the vertex if they are to have any chance of coming back and closing up into a 2k thing. So in this sum on the top, I can just replace our whole graph H with these balls that have radius k. And also, I haven't told you yet how I choose my k, so we are completely free to choose it as we wish. And the way we will choose it is to make these balls small so that we can use lemma 1 on them. Okay, so wait, I went in the wrong, what's happening? What? Yes, so I'm removing this, derivation. So what we get here is, something is, okay, I understand what's happening. So I just plugged into this expression, into H, I plugged in the ball instead of the graph H. And now I use the variational definition of lambda 1, namely that like any quadratic form of this form is always smaller than the largest eigenvalue of that subgraph. So if we pick this k to be small enough so that we can guarantee that this ball is small enough, then lemma 1 will tell you that actually this is at most lambda 2. Right? Lemma 1 says that any small subgraph needs to have its largest eigenvalue at most lambda 2. Unfortunately, it doesn't tell you it's a bit smaller than lambda 2, because the lambda 2 bound here is stupid. Well, I mean, what it tells you is it gives you n times lambda 2 to the 2k, so you get an n bound on the multiplicity, which is trivial and gives you nothing. So what we really want here is something just a tiny bit better than lambda 2 as an upper bound on this lambda 1. And this is where this sort of stronger Nikiforov lemma is going to come into play, because it's going to give us this little bit of extra boost. So really, instead of ensuring that just this ball has an upper bound of lambda 2 on the lambda 1, I'm going to ensure it on a bit bigger ball of radius k plus 1, and actually on one in the original graph G rather than in this deleted graph H. So again, I can do this because delta is the max degree in G. So this ball will have size at most delta to the k plus 1. So if I pick k to be at most, I should have a 1/2 here in front of log delta n. Then this ball will have size at most root n. So lemma 1 will tell you that if this is not true, this upper bound of lambda 2 here, then you just trivially get like root n bound, which is way better than anything we're aiming for. Okay. So I have this nice upper bound of lambda 2 on a slightly larger ball in a slightly bigger graph. So now I want to say that that tells us that this lambda 1 needs to be a bit smaller than lambda 2. And this is where lemma 2 will come into play. So we will apply it to these two graphs. One is this larger ball in a bigger graph, and one is this smaller ball in a smaller graph, right? It's a subgraph of this for sure. And also, if you kind of think about it for the moment, this way that we defined it as a kind of, because we deleted all of the centers of the stars when we went from G to H, it will actually ensure that, so kind of the leftover not participating in the stars has a max degree of lambda 2 minus 1 in our graph, because we deleted all the stars. And if you have a max degree of lambda 2 minus 1, that is sort of the condition that we want in lemma 2. And all of the leaves of the stars will get deleted by deleting the boundary, because we're putting back these vertices from n when we are comparing these two graphs f and k. So we can apply our lemma 2. The condition is satisfied, and it's kind of precisely built to survive this condition. And then we get a sort of upper bound that is just absolute powers of lambda 1. So specifically, kind of you get that lambda 1 of f is by some kind of absolute power of 1 over lambda 1, smaller than the lambda 1 of k. And k here is, right, the one that we have a lambda 2 upper bound on. And this bound is the one that we see here and that we want to beat lambda 2. So again, we can take roots here, and this costs us nothing. So again, this takes a little bit of verification, but this is how maths works. And now we can just plug in the lambda 2 upper bound that we ensured by picking our k not to be too large. And we get an upper bound of this form, which is lambda 2 minus some polynomial in 1 over lambda 2. And now we plug that in on top. So we have the multiplicity times lambda 2 to the 2k, that's the left-hand side here. And the right-hand side is just n times lambda 2 to the 2k, that's this term taken to the power 2k, times this term to the power 2k. But the thing is, that's kind of the power of the trace method. By taking this k large, you make this small gain actually quite substantial. I mean, of course, there is a bottleneck, and this is where the kind of the barriers are now kind of coming from, because on one hand, we need it to be small enough so that we have this bound so that we can actually start from there. But also we want it to be as large as possible so that we actually get a nice improvement here. So again, let me cancel out. So what I'm doing is canceling the lambda 2 to the 2k terms, which are on both sides. And what we're getting is n times this term, and I want this term to be small. Now this term is just some e to the minus k over lambda 2 to the 4k. So if I pick k to be at least lambda 2 to the 5, I'm doing amazingly well. Why? Because now this is an exponential thing in lambda 2 at least, so it's n over e to the lambda 2, and we're aiming for n over lambda 2, if you remember. So this is actually doing extremely well in this case. And the reason we have this n over lambda 2 plus 1 showing up is because of the Cauchy interlace and the deletion of the centers of the stars in the second step here. And that's it. That's the whole proof. So you now kind of balance out these two bounds and you get that kind of lambda 2. So for these two inequalities to be able to simultaneously be satisfied, you need lambda 2 to be smaller than something like log delta n to the 1/5. And if you do that, you get immediately a bound, which, as I've shown you, would be something of the form n over lambda 2 plus 1 plus n over e to the lambda 2 or something like that, which is much, much smaller than the first term. And again, if you're a bit more careful, you can save on this and you can kind of get rid of this second term and various things you can do much more precise.
Matija, can I ask? So one thing I didn't quite understand here is, so how are we using the fact that in H we deleted all stars of size lambda, well, maximal collection of stars of size lambda 2. So that in F all the degrees are small, or?
So we are using it so that we can apply lemma 2, but it's not quite that we get degrees small, because we can only afford to delete the centers, not the whole stars. Right? I can only afford n plus 1 vertices. So I'm only deleting the centers. So the leaves still remain, but I'm claiming these leaves will be in the boundary of this graph F compared to the graph K. So that when you do our version of Nikiforov lemma, which deletes the boundary, they all get killed in a single.
So after all, so we basically, in the graph that we care about, we have small maximal degree.
You have a small maximum degree once you delete the boundary.
Once you delete the boundary, you have small maximal degree.
And the small maximum degree is enough to give you an upper bound on the largest eigenvalue, and that is like at least at most lambda 2 minus 1, which is what lemma 2 wants. So you get the kind of improvement. As soon as you delete that boundary, it kind of shrinks down by a bit. And then kind of instead of, so in this argument, you can just plug in directly Nikiforov with the diameter, and you would get a double exponential requirement.
And can I ask another, like, I mean,
Sure,
a
yeah, of
bit
course.
speculative question? So, if in this second bullet, instead of taking a maximal vertex disjoint collection of stars, so which you say is the reason for this lambda 2 plus 1, right?
Mhm.
N over lambda 2 plus 1. What if we'll take, I mean, what if we're aiming to use this more general version of your lemma with this second neighborhood or third neighborhood? Then here you can take something sparser, supposedly with fewer, like better bound, right?
Yeah, you can, instead of stars, you can take balls of a certain radius.
Yeah.
And
And
but
you
the
will have
question
fewer of
is kind of
them.
how fast these balls grow. So
Uh-huh.
somehow this is precisely how we're kind of saving this little bit of extra that kind of shows up. But somehow in these graphs, we only really have connectivity. If you tell me that kind of these balls
Mm.
grow nicely, you can
Mm-hmm.
start saving a bit on that bound.
Yeah.
But there are trade-offs, right? And there is no
Yeah.
guarantee really that you will not have like these balls and then kind of sort of these long paths that link them up somehow. So the stars are actually somehow like, think of them as cliques, roughly speaking.
Mm-hmm.
And then there is this lollipop graphs that kind of connect them. But you're precisely right. Like there is like there should definitely be more space to kind of do things here. But somehow, and this is also actually how this n over log log n graphs look like, to be fair. So they are precisely cliques with long paths kind of joining them, and they build some expander in between of them, because there is some actually trade-off here between that it needs to expand on a large scale, otherwise you will win, but it needs to not expand on the local scale because also you'll win otherwise. So you're sort of
Mm-hmm.
forced to
Mm-hmm.
look something like that. But there is definitely a lot of space here, and I think there is space to do something for sure, but somehow like these constructions do show you that you need to do something more clever, and somewhere
One
like
has to be very careful, yeah.
start using non-analytic stuff, because every inequality here more or less works even if lambda 2 is something close to lambda 2. The only exception is lemma 1 actually. But if you
Mm-hmm.
go back
Mm-hmm.
to that lemma 1, it's a bit harder to do it if you are working with something that's like a little bit under. But yeah, there is
Mm.
one course, but let me not.
Yeah, and another thing, another question, then what about the randomness? You said that you're using randomness
So this
somewhere,
is for
but
the other theorem. So here there is no random. So in the other theorem, instead
okay.
of doing the stars, we are going to delete a random set of vertices. And of
Mm-hmm.
course, you can do both. Nothing is stopping you really from doing both. But somehow in this case, randomness doesn't work very well if you, it's just a matter of regime. So somehow um, like these are very sparse graphs in a sense. And then it's hard to guarantee certain. I at some point tried, and kind of the randomness in this case is sort of doesn't work very well. But well, it will give you something, I think, actually, even still, but it will be a weaker bound than what this is giving. And I've never actually compared it to what was known before. But yeah, but this definitely kind of beats the random one. But once you are a denser graph, then kind of deleting vertices starts to work much better, because you kind of have a much better chance of actually kind of ensuring that what you randomly deleted will kind of deal with your boundary vertices in a sense. So this is intuition of kind of for me at least, why kind of randomness starts being correct around log and
Mm-hmm.
but the kind of the dense case is the one that is kind of more open now. Then since we know at least in the equiangular lines, we understand the answer for what corresponds to sparse regime here.
Okay, thank you.
So I just have a final slide, which is just let me just kind of put it on display, which is just kind of summarizing a little bit of what we said, and puts this very nice conjecture, which I like a lot, which is that this n over lambda 2 plus 1 bound should actually, in my opinion or belief, be true all the way up to polynomial maximum degree. So we can prove this for up to small polylog degree, but it should actually be true all the way up to n to the little of 1. And I think that is a very nice open problem and would be a very nice clean statement. So thank you all very much for your attention. I'm sorry for going a bit over.
Thanks a lot, Matija. Yeah, it's for the time, it's totally fine. So we don't really have a strict limit. So yeah. it's great that you gave all these details. I think at least I enjoyed it a lot and learned a lot.
Thank you.
Thanks a lot, Matija, and yeah, great results, and hope to see you sometime soon on the conferences.
Likewise. Thank you very much for listening. Thanks for all the questions.